Now it's time to talk about one of the most iconic experiments of all time, the Young's double-slit experiment. So Thomas Young performed this experiment in 1801. This experiment literally changed the way the world viewed light itself. The setup of this experiment was extremely simple. All he had was a source, two slits, and a screen on the other side. Now, if you asked any normal person, or anyone actually, what they'd expect to see on the other side, you or that person would say that, yeah, there should be some sort of brightness, right? And the area that's commonly illuminated by both these slits should be slightly brighter, and the other areas would be comparatively darker. That's what you'd say. But let's see what really happens. So now, let's try and explain the weird observations that we saw in the Young's double-slit experiment through the model of wave optics. So first, let's quickly go through the setup. Now, there is a point source S. It's a monochromatic point source of light. After that, there are two slits, S1 and S2. So they are horizontal slits. So if you look at the front view, they look like this. And from the side view, they'll basically look like 2 point sources, or just 2 points, S1 and S2. And of course, on the other side, there's a screen. Now, one thing to note is that the point source S is placed in such a way that it is equidistant from S1 and S2. Okay? Now, what would happen? Now we know that the point source S, because it's the source of light, it will produce spherical wavefronts, right? Now, when these wavefronts, when they hit the slits S1 and S2, what will happen? So we know that from Huygens principle that every single point on the wavefront acts as a source itself. So therefore, these two slits will produce cylindrical wavefronts. In fact, if you look at the front view, these wavefronts will look like this, right? And from the side view, if you consider a plane of cross-section, they'll basically look like this. You can see that these wavefronts will look like circles that are expanding, right? Very similar, in fact, to ripples on a calm surface of water. Now, the obvious question is, what happens when these wavefronts intersect, when they touch? They will interfere. So now, let's consider a point on the screen P, which is equidistant from S1 and S2. Now, what would happen over there exactly? So obviously, because S1 and S2 are the sources, they will produce waves, but there'll be only two waves that reach P, right? One from S1 and one from S2. So S1 and S2, in fact, will produce infinite waves in all directions. But we don't really have to worry about all that. We only have to worry about the waves that are reaching P from S1 and S2. So if I draw a line, right, S1P and S2P, I'm only worried about those two waves that are coming from S1 and S2. Okay? Let's also analyze these waves a little. Now, first of all, these waves are electromagnetic waves. They're not mechanical waves like the ones we considered in the previous case. So they are basically waves of varying electric and magnetic field, right? So of course, let's not worry about the magnetic field right now. So let's only talk about the electric field. They are waves of varying electric field. Let's say that the amplitude, right, of both these waves is the same, and let's call it E0. Also, when they start from S1 and S2, they will be in phase because they are equidistant from the source, right? So from the waves that start from S1 and S2, they will start in phase, okay? Now, what will happen when these waves reach the point P? It will obviously interfere, right? Because there are two waves intersecting at that same point. So this is slightly different again from the previous case. In the previous case, we considered two waves that are traveling in the same string. But this is analogous to two waves that are traveling in two different strings that are intersecting at one single point. So the interference will still occur at that same point. So if I had a device that measured the electric field at that point, what would it measure? It would basically measure the sum of the individual electric fields contributed by both these waves. Okay, fine. And what would be the amplitude of the electric field at that point? Now that depends on the path difference. What is the path difference between these two waves? it is 0, right? Because you can see that S1P should be equal to S2P. So if the path difference is 0, then they will basically reach in phase, right, at that point P. So at every single point in time, the resultant field will be twice the field contributed by each of these waves because they are in phase. So therefore, the amplitude will be 2E0. And what kind of interference is this? Now, this is obviously constructive interference, right? Because the waves that are interfering, they're in phase because the path difference is 0. Now let me try something different. What if I move that point P a little up, a little above? Now what will happen? Now obviously the path difference will not be 0 anymore, right? Because the wave that's coming from S2, the path it's taking will be longer than the wave that's coming from S1, right? So there will be a path difference, which means there will be some phase difference as well, right? And when these two waves interfere, what will be the amplitude? I don't know. That depends on the phase difference, okay? But what if I move it up? What if I move this point P in such a way that the path difference equals lambda by 2, right? So I move this P up, I bring it to a point such that S2P minus S1P equals lambda by 2. Then think about it, what will happen? So if you can imagine two waves that are coming from S1 and then S2, right? Both of them are traveling with the same speed, but S2P, basically the wave that's coming from S2 will take a longer time, right, to reach there because the time taken, or rather the path is longer. So S1P, or the wave that's coming from S1 will reach first, okay? But S2P will reach a little later, but with what difference? With the difference of lambda by 2. That means there will be destructive interference, right? So if you look over there, they'll reach in such a way that the field contributed by the wave from S1 will always be negative of the field contributed by the wave from S2. So the net field at that point will always be 0, or the amplitude, but at that point will always be 0. So this is destructive interference. Okay, this is interesting. Now wait, what if, okay, let's assume that if I keep moving this point P further and further up, okay, I assume that the path difference will only increase. If I make that assumption, okay, then at a particular point P, again, if I move it up, there will be a point where S2P minus S1P equals lambda, right? So that basically means the path difference equals lambda. Then what will happen? Then obviously the wave from S1 will again reach first, but the wave from S2 will reach after some time, but just after the first wave has finished 1 lambda, right? Or basically the phase difference will be 2 pi. But we know that this also corresponds to constructive interference. We know that the net amplitude will be 2E0 in this case. So, okay, so that means we'll have constructive in the middle, then destructive, then constructive again. Okay, this is interesting. Also, this will be exactly true for the bottom as well, right? If I move, instead of moving P up, if I move P down, exactly the same thing will happen, right? Because it's symmetric. So there will be a constructive interference, a point with constructive interference exactly at the center. Above that, there'll be destructive, then constructive. Similarly, below that, there'll be one destructive point and then a point with constructive interference. Okay, so now that we know this, let's do something else. Now, let's see what happens if I move this point P even further up. Now, if we stick to the assumption that as we move this point P up, the delta x increases, then at some particular point, the delta x will become 3 lambda by 2, right? What will happen there? Then that will mean that at that point, we'll have destructive interference again. Now, if I do the same thing again, if I move it further up again, delta x, there'll be some point where delta x equals 2 lambda. Then at that point, we'll have constructive interference again. And once again, the same is true below as well, because it's symmetric. So you can see that there's some sort of a pattern we find here, right? Where there is, in the center, we have constructive interference. Then as we go up, there's destructive, then there's constructive, then destructive, etc., so on and so forth. In fact, the pattern will be such that at all points, where delta x equals n lambda, there will be constructive interference, and at all points where delta x equals 2n plus 1 into lambda by 2, there will be destructive interference.